So EMI, electromagnetic induction. In this, now we are going to discuss. Already we have discussed yesterday motional EMF. Okay, motional EMF in a magnetic field when a loop is entering and moving out with some velocity v. Therefore, we found an expression whenever it is entering with the velocity v, it is having the length and it is moving here and back, to and fro like this. Therefore, the current producing in this, whatever the current is producing in this, that is nothing but EMF is inducing in the loop. That expression we have written, that is EMF equal to minus BLV we have written, right? Now, let us see if the same motion EMF in the rotational motion, if you take it. Rotational motion in the sense, let us say a rod is rotating. A rod, where it is rotating? In the magnetic field, right? When a rod is rotating, which is having the radius capital R, this, and rotating in the magnetic field in circular form. Means, let us say its initial position O at this point, it has made angular displacement theta equal to omega t. We know that omega is the angular velocity, omega equal to theta by t. Therefore, theta is the angular displacement in the sense theta equal to omega into t. We can write. We have learned this is from the 11th standard circular motion as well as rotational motion. Now, whenever this rod is moving, of course, the rod not only here to here, let us say it is displacing. Okay, it is displacing. If I'll consider it is displaced theta, then theta equal to omega t. If I'll take it is displaced d theta, means small amount of displacement has taken place in the circular form, right? Therefore, with respect to that, since it is having the radius r, and from here to here, let us say particle in the sense when radius vector is here, in this direction the linear velocity will act, and radius vector here, in this direction the linear velocity acts. Means from here to here, the direction of the linear velocity changes, right? So always linear velocity acts tangential to the circular motion. Now, in this, whenever it has moved, so here angular displacement is taking place about a point O, and at the same time perpendicular to that angular velocity also we will take omega. Now, how can we represent? How can we find the EMF here? Since it has displaced, then it is produces small EMF dE equal to what we can write. The magnetic field remains same and it is displacing along its linear velocity. So I can write dv into dr. V for velocity, dr for the length. Dr in the sense here velocity of the particle from here to here it has changed, right? That means here we can take linearly it has displaced from here to here, right? So linear displacement dr we are taking. Let us say if I am differentiating this, then in the form of differentiation, I got dE equal to d into V into dr. This is for small EMF which the particle has displaced from one place to another place. The same particle displays along the circular motion or the rod, let us say, or the rod is displaced along the circular motion continuously, then it produces circular motion. Due to the circular motion, it is disturbing the magnetic field. Since it is disturbing the magnetic field, in a sense, there is a change in the flux takes place, right? We know that change in the flux produces EMF. So, due to small displacement of a rod in a magnetic field, then small EMF produces. For example, if the rod completes the circular motion, then the total EMF produced by the rod which is moving in a circular path about a point O can be written as dE is nothing but integration we can write up. Integration of dE we can write up E, which is also equal to integration of V into dr I can write up. Okay. Now further if I'll take this is V is common. In a place of V, we have a relation between the angular velocity and linear velocity. V equal to r omega. Here r is a radius vector. Let us I'm preparing to take capital that is a radius vector. If I take radius vector omega r, instead of writing directly r omega, here since I have the variable dr, I am taking first initially r omega, then I am substituting 0 to r is a limit. In the place of v, I am writing r into omega into r. Therefore, it becomes r square, right? So, omega into d outside, r square into dr inside. Sorry, not r square, r into dr. R into dr. Now, r into dr I got. We know that integration of x into dx gives us x square by 2. Since we are having the limit same way, r into dr equal to r square by 2 I can write. So limits 0 to r in the sense 0 final limit minus initial limit in the sense I am taking this is r square by 2. Right? So if it is r square by 2, what I can write according to this formula, then whatever EMF I wanted to find which is in the rotational motion, that I can find here E equal to B into omega into r square by 2. So this is a EMF produced in the rotational motion of a rod which is rotating about a fixed point in the magnetic field. Okay, this is a in the linear motion. Just what is in the linear motion? E equal to minus dl. This is also motional EMF, but it is in a rotational motion. So omega is a angular velocity, r is a radius vector, this is b is a magnetic field. This is nothing but motional EMF in the rotational motion. We have a numerical for this. What is the numerical example numerical for this? A wheel, a wheel with 10 metallic spikes, each 0.5 meter long, is rotated, is rotated with a speed, of 120 revolution per minute in a plane, normal to the horizontal component of Earth's magnetic field. Earth's magnetic field He at a plane. Okay? Place sorry, at a place. If horizontal component of magnetic field equal to zero point 0.4 Gauss at a place, at a place, comma, what is the induced EMF between the axle axle and the rim of the wheel, question mark. Here we know that 1 Gauss equal to 10 to the power of 4 Tesla. First, we need to understand the question. A wheel means a cycle wheel like that, bicycle wheel. A wheel with 10 metallic spikes, each zero point 0.5 meters long, is rotated with a speed of 120 revolution per minute. 120 revolution per minute. So now, in this 120 revolution per minute, how can we express what they are telling? If it is moving with 120 revolution per minute, a plane normal to the horizontal component of Earth's magnetic field, HE, at a plane normal to the horizontal component of Earth's magnetic field. Normal to the horizontal component of Earth's magnetic field in the sense that is like this, completely vertical component. This is a horizontal component of the Earth's magnetic field. Okay. So with respect to that, it is making 90 degrees in the sense it comes in the vertical position. So HE is given 0.4 Gauss at a place. What is the induced EMF between the axle and the rim of the wheel? See, this is a wheel, this is the axle. Okay, like these spikes are there. Understood? So induced EMF they are asking us to find. EMF equal to, since this is acting like a rod in a circular motion in the horizontal component of magnetic field, means like in a form of vertical, this is horizontally is rotating. Now half into B, magnetic field how much it has given? 0.4 into 10 to the power of 4 Tesla. Next, it has omega. Omega can be written as how much here? Omega equal to 2 pi n or 2 pi frequency we can write. 2 pi into n. N means what here? N in the sense how many times it is rotating per minute, means 120 revolution per minute. 120 revolutions in the sense 120 by 60 if you do, how much? Hello?
Yes, sir.
Yeah, 120 revolutions per minute in the sense
By 60.
60 seconds.
Yes, sir.
Then it will be 2,
2.
right? So
Yes,
2
sir.
pi into 2 I can write as 4 pi. Therefore d omega 4 pi. Next, radial distance. How much that radial distance is given in the question? 0.5 meters for 10 metallic strips, right? So 0.5 we have to write into 0.5 whole square now, since it is r, 0.5 whole square. Then what is the EMF? 2 1 ja 2.2. Next, we are having 10 to the power of 4. 2 into 10 to the power of 3. 4. 2 4 the 8. 5. I'm taking here. Then I'm writing here 0.5 into 0.5. 5 into 10 to the power of minus 1, right? So 25 into 10 to the power of minus 2. Can I write like this? So minus 2, 3, 1 gone. 1 10 left here. So it can be given uh, 80 into 25. 5. Of course, 80 into 25 can be written in terms of 200. Can we? Means 2005. 2005. This 2000, if you multiply with the 3.14, then you will get the answer 3.14. Of course, this if you are removing decimal, this if you write 10 to the power of 4 into 4 or 5, the three zeros are there. Okay, 2000 into 3.14, 3.14, 314 is 628, right? And
Yes.
zeros as usual. A decimal after 2 points it is there. After 1. So how can you
Six
write?
two eight zero
628
zero.
into 10 to the power of 3. This is if I write in terms of decimal. How can I write? Point. Have to make it as in a form of decimal. 6.28. 1, 2, 3. 2 decimal. 6.28 into 10. Anything anywhere is missed. This is 0.5. 5 into 2. How much? In the power of 2, no? 2, right. In the power of minus 2 only this is.
So 2000 into 3.14. So there will be two zeros will go in the decimal point. So it will become 6280.
6280.
Yes, sir.
Okay, 6280 I wanted to write in the form of powers.
So 6.28 into 10 raised to 3.
Yeah. In terms of standard value, we have to write that. Everything is counted, no? Nothing is missed, no?
Yes, sir.
Yeah. Then this is the actual method we will use. Here 10 metallic spikes you are using. So if you are using 10 metallic spikes in the sense number of spikes if you are counted, but still it is same only, right? Next, one more most important concept here, energy consideration. What do you mean by energy consideration? Means whatever the EMF which is produced in the motional EMF case. I mean, when a coil is moving in the magnetic field to and fro, or by the motion of the coil in magnetic field, whatever the EMF has produced, that in that loop, if you are considering resistance, let us say, the coil is having the resistance obviously according to the Ohm's law, some amount of energy is dissipates with respect to the energy, right? And at the same time, you should remember one important thing is that when the rectangular loop is moving here and inside and outside, so across the loop, what it has produced, current it has produced, right? From here to here whenever it has moved. So whatever the currents are generated to this loop, then that we can write as I equal to the EMF induced in the coil by the resistance in the coil, which we are considered resistance across the. Of course, here whatever the this considered length is there, that I am considering. Rest of the also having the resistance, but this resistance is negligible in front of this resistance. Okay, in such a way I am considering here. So I equal to E by R. Since I have considered that, we know from the motion EMF case, I equal to BLV by R, right? This is B, this is R, remember. Now, as I said, since it is having the resistance whenever it is moving inside and outside, obviously it consumes some amount of power, right? Before consumption of the power, you need to understand one mechanism how EMF produces in the conductor. If let us say this is a PQ conductor in the sense, whatever the electrons are there and positive charge carriers are there, they'll move away from each other. See, all the charges, all the positive charges accumulated here, and all the negative charges accumulates here. Therefore, here to here the potential difference created, right? Where these charges were, the charges actually inside the conductor only. But why these charges get separated? Because of the Lorentz force. With that, because of the Lorentz force. We studied in magnetic effects of electric current. When a current carrying conductor or a charged particle is left in a magnetic field, it experiences a force, right? So here, whenever I left inside, it experiences a force, and I'm not talking about the conductor even. Inside the conductor, whatever the charge particles are there, this charge particle has experienced the force. Due to experiencing the force, the charge particles get separated here. Get separated, therefore, there is a potential difference has created as a positive and negative like this. Means this is negative in the sense this is positive. We can give for that. Because potential difference is created if you connect a wire to this current flow takes place. This is happened due to the Lorentz force, right? So the Lorentz force F equal to what we have studied. Lorentz force F equal to BIL, Bill or Bill sine theta we say. So since here which is carrying the current I is in the motional EMF of the loop or conductor is I, and the product with that magnetic field and length of the conductor gives us bill that is called as Lorentz force F. If I substitute in the place of this B into I, if I substitute here B square L square V as this and R as this. And so this is a Lorentz force which I got. As the way since the resistance is used, I told just now, this power dissipation takes place. Power dissipation means some amount of energy is wasted in the form of heat energy because of the resistance. So here this is happen. This is happen here since the rod is moving with a velocity v inside with some constant speed, then it is also experience Lorentz force at the same time, and also against that is it trying to move inside. So power dissipation can be written as here this is a power dissipation. Okay, here two types of powers are we have to take. What are the two types of powers? Before going to the dissipation, power consumption I have to talk about. Power consumption is nothing but the power which is used, or I can say due to the external force whatever the power has produced. Okay, power required or this power is required to move a conductor inside the magnetic field. Sir, why you need sir power inside the magnetic field? Because this is required to against this force. So against this force in the sense you need power to push up. So therefore you need to apply some external force. That is the external power. We can say that P equal to what we can write up I square R. So P equal to I square R in the sense I is how much we have. We know this, of course, P equal to I square R. If you go here, there is a different problem arises. R is resistance which disappears the power. So instead of I'm going this formula, I'm going with the instantaneous power which I have applied by the external force. Why I have used, sir? You could ask me a question. Instead of that formula, why I'm using this? This is the force I'm using to push or to push the conductor inside the magnetic field. Okay, against the Lorentz force which is developed inside the conductor. So F, what is the F? We got above B square L square V by R into V. Therefore, it becomes D into V. I can write as D square and down R as this. Sir, you have taken the same force. Of course, the same amount of force I need to overcome here. So for that purpose, I need external power to push the conductor or power required to push the conductor by application of external force. Right? So that's why same amount of force I need to overcome. That's why I have used the same. So this is a power we have generated or we required, we say instead of generation we say here power required to do this. Now power dissipation, just now whatever I spoke, power dissipation comes due to the dissipation of energy in the form of heat. Okay, so that I'll write pj. Why pj I'm writing in the sense that is a Joule's law of heating effects. We studied H is directly proportional to I square RT. Therefore, Hj equal to I square RT, where j equal to 1 we say. So, same manner, Pj equal to here I square R we will write. R is a resistance of the conductor or wire which we have used in the loop. That is Pj equal to also same I square in the sense B square L square B square by R and this R. Okay, of course this is square, this is R. In this and this square get cancelled, you have R. So this is a power dissipation. You can find here the power dissipation is same as the power required to push the conductor in the magnetic field. Okay, what did you find here? Power dissipated as a Joule's heat is same as the power required to push the conductor inside. So this is all about the energy consideration we can say. Now, the same manner, how can we express how can we express the mechanical energy whenever is converting into the electrical energy? That is nothing but which we have seen till now. We have applied a force, external force to produce or to raise some power in the conductor against the Lorentz force. We pushed, right? Before that, since due to that also, inside the conductor, automatically there is a Lorentz force has developed that trying to resist against that we have applied force. So here two types of forces are there. That's why the second force, whatever we have taken, that force we have considered in the to push the conductor inside the magnetic field. We need to have some power. That power is the initial power, and at the same time, while this process is going on, the another power has produced. That is which is power dissipation. PJ we say. Now from this same concept, Since mechanical energy has, because of pushing, you have applied force. That is mechanical force. Is converted into the electrical energy. Same way, we are going to express EMF in terms of charge. Okay, the magnitude of EMF is equal to change in the magnetic flux with respect to time, right? This expression further I can also write, this is a part. EMF or voltage equal to I into R, I can write up, I can, so now I also I can write as dq by dt into R, I can write. Now at the same time, this is equation 1, let us say, this is equation 2. This is EMF, this is also EMF. If I'll equate 1 and 2, then I can write dq by, sorry, d pi by dt equal to delta q by delta t. So into R. Therefore, this expression I can write mm, delta pi by R equal to delta q. Means the flux, the change in the flux in terms of charge and resistance we are expressing here. Simple is that. Okay. Here, which flux is we are talking about? Magnetic flux. Remember, magnetic flux. Again, if you see the charge, then you get different flux. No, it is magnetic flux. Okay, because change in the magnetic flux only produces the EMF or current. Okay, this is one important expression, like EMF expression in terms of charge. Of course, we have discussed yesterday in terms of charge, in terms of current, and in terms of voltage also we have discussed. Right. So next.